Okay, we'll continue discussing feed-forward network and backpropagation. So last time we looked at derivatives, which is a very important discussion because the whole training algorithm is based on gradient descent. And in gradient descent, you remember the starting point is the partial derivative of the loss expression or the error expression with respect to the parameter or the weight that we are interested in changing. So we derive the derivatives of sigmoid function. Derivative means the derivative of the output with respect to input. So for sigmoid, the derivative has a nice form, output into 1 minus output. For softmax, the derivative are obtained in two cases. The first case is that of derivative of the output with respect to own input, which is like sigmoid, output into 1 minus output. And since the softmax function depends on the net input of all neurons, okay, so the derivative with respect to the input of another neuron is also important. So there the derivative came out to be minus output of the neuron in concern and the output of the neuron whose input we are considering for taking derivative. Okay, both expressions are quite nice. And output, it is only the output which is involved in the expression. So from these, we derive the weight change rule in case of the softmax and cross entropy combination. The basic rule is gradient descent. We have seen that gradient descent is a greedy algorithm. Okay, so if the gradient is negative, the weight change is positive, so that the operating point moves in the direction of reduction of error. If the gradient is positive, then the weight changes in the decreasing direction, so that again the weight reduces. So it's a greedy algorithm and therefore it can get stuck in local minimum. Now, genetic algorithm is sometimes used to fix the initial values of the neural network, okay, by what is called mutation crossover these operators. So that is another interesting discussion. Now, when we use single sigmoid neuron and cross entropy loss, the cross entropy loss is minus t into log O minus 1 minus t into log 1 minus O. This is for the two-class classification problem. T is the target value, O is the observed value. So remember, cross entropy is negative of target distribution log observed distribution, summation over all the classes, summation over all the data points. So when we take this loss expression and take the and consider one particular weight, then the change in weight expression comes out to be learning rate into target minus observed into the input on that connection. So it is independent of the derivative of the sigmoid function. Okay, so this is an attractive proposition for cross entropy softmax combination. The station derivative does not figure in the expression. So when we take multiple neurons in the output layer, and these neurons are computing softmax. So softmax gives me an observed probability distribution. We have to compare this with the target probability distribution. So here again, the weight change expression comes out to be equal to a learning rate into target minus observed value into input value on that particular connection, just like sigmoid. Okay, and this happens because you will have to consider the self-derivative and also derivative of other neurons. Okay, other neurons which are participating in the softmax expression. But the sum and substance is that the weight change expression is again independent of the derivative of softmax. Okay, so these things you will have to implement in the lab to make your understanding clear. So we have this nice situation when the loss is cross-entropy loss. The change in any weight is learning rate into difference between target and observed output and input at the connection. Weight change rule with total sum square loss. Again, the principle is same. And the weight change expression involves learning rate into target minus output. Input on the connection is fine, but here the derivative of the sigmoid figures in. Okay, so this comes due to the chain rule of the derivatives applied here. It comes from this expression delta O delta net, where O is the output, net is the input. Why delta O delta net did not contribute anything for cross entropy? That is because this delta L delta O multiplied by delta O delta net cancel the contributions from the derivative of sigmoid. And delta net delta W1 contributes the input value on the connection. Okay, this is how it operates. Now, when you have multiple neurons and we have to use total sum square loss. Here again, total sum square loss is computed over all the neurons in the output layer. And the change in weight expression is learning rate into target minus output into station derivative, which is derivative of the sigmoid, multiplied by the input on the connection. Okay, just like sigmoid neuron. Now, in case of total sum square loss, there is no mutual dependence, okay, between the, I mean, no output depends on the input or output of other neurons. Okay, error depends on all the outputs, but the output as such from a neuron does not depend on the net input of any other neuron. Okay, the neurons are independent of each other. So that's why this weight change rule is applicable to all neurons where there is no hidden layer. Learning rate into target minus observed, station derivative into input at the connection. Now let's go back to backpropagation because we justify this name backpropagation because of the hidden layer. It is the hidden layer which requires backpropagation. So let's look at this expression. These were briefly touched upon in one of the lectures before. So we have this weight here, WJI. J is the destination neuron, I is the source neuron. Okay, and we are interested in finding out the change in weight for this. So the derivation goes as follows. By definition, delta WJI is minus learning rate into delta E delta WJI. Eta is called the learning rate. It is between 0 and 1. Now, E does not depend on WJI directly. So we'll have to apply chain rule of derivative. So delta E delta WJI is delta E delta net J into delta net J delta WJI. Now, a bit of digression for 1 or 2 minutes. Some of you have come and asked me, where is this material on backpropagation from? Okay, now this particular material, gradient descent equations for sigmoid neuron. Okay, this is from a book called Parallel Distributed Processing by McClellan and Rumelhart. Okay, so that's a very classical book on neural network-based computation. So this particular material is from there. But the point is, the derivation for Softmax cross-entropy, these evolved over time, okay, from my teaching of the course. And those are not exactly derived the way it is done in the slides. I don't think you will find it anywhere. Okay, the emphasis of the point that Softmax and cross-entropy, they sort of cancel each other, and so that the station derivative does not appear in the weight change rule. These you do not find directly as such. So your best bet will be to depend on the slides which are given to you. And I think they are well done, okay, pretty clearly expressed. So many of these neural network discussions you really don't find in textbooks or research papers. They've evolved over time from the experience of teaching the course. So, but this particular material is from Mactilland and Rumelhart, parallel distributed processing. Now, this particular quantity, delta E, delta net. Okay, the partial derivative of the error or loss with respect to the net input to a neuron, for which we are interested in finding the weight change rule. This quantity plays a very important role, okay, in whole of deep learning. The derivative, partial derivative of the error with respect to the net input. And again, if you see the neural network textbooks, research papers, it is not emphasized the way I am emphasizing it. Okay, this quantity delta E, delta net plays a very critical role in whole of deep learning. Okay, and what is the description of this? The description of this is the rate of change of loss with respect to the net input to any neuron. In particular, the neuron whose connection weight change we are interested in finding. Okay, now delta A, delta net J is given this notation of minus delta J. So the change in weight expression is eta into delta J, where J is the destination neuron, and OI is the input at the connection. Okay, I is the source neuron. So the change in weight is eta into destination neuron something and source neuron something. Okay, so this is the universal rule of backpropagation. Now we can use this expression, general expression, for finding out the weight change in the outermost layer. So in the outermost layer, remember that we are interested in this quantity delta J, which is minus delta E, delta net J. So minus delta E, delta net J can be written as minus delta E, delta OJ into delta OJ, delta net J, because E does not depend on net J directly. It depends on O. So E is equal to half Tj minus Oj square. So this should be J. J going from 1 to N. So for outermost layer neuron, delta J becomes delta E, delta net J, which is minus delta E, delta Oj. This becomes minus Tj minus Oj. If you take this expression and take derivative with respect to Oj, it is Tj minus Oj. And delta Oj, delta net J is the station derivative, the derivative of the sigmoid. So the change in weight expression is eta Tj minus Oj, station derivative into Oi. By the way, the expression is very general. You take any function on the neuron, the station derivative of that function is involved. So if you take a linear neuron, for example, and let's say y is equal to mx plus c is used, then the station derivative will be just m. Yeah. Okay, so there is a general expression. So for the weight change rule in the outermost layer, any question from anybody? No. So now we can make some interesting observations from the weight change expression. Weight change expression is eta into target minus observed into sigmoid derivative into input on the connection. Let's see when the change in weight tends to 0. Almost no change in the connection weight. If OJ equal to TJ, this is intuitive. If the observed value is equal to the target value, why should there be any change in the weight? Okay. If OJ tends to 1 and or OJ tends to 0, that is coming from the sigmoid derivative. So this happens when the input value for the neuron is extremely large. Okay, either extremely large negative or extremely large positive. So this behavior is called the saturation behavior. The sigmoid curve is the sigmoid curve has a saturation behavior, right? Minus infinity tends to 0, plus infinity tends to 1. And the derivative becomes very small. So for OJ equal to 1 or OJ equal to 0, the derivative is almost 0. And therefore, the change in weight is also very small. The other interesting observation is that if the input to the connection also is 0, then there is no change in weight. So this is called the credit or blame assignment situation. If a particular input value is 0, it is not contributing anything to that neuron. So the neuron's output is not affected by that input. Therefore, that output does not contribute to the final error. Okay, so this is called credit or blame assignment because let's say a company is making profit. Okay, then we know that this profit is proportionally not the whole profit. A part of that profit is proportionally distributed to various employees in the organization. Who has contributed maximum to this profit? This person should be rewarded most. So the input of the neural network, which has highest value, typically bears the maximum brunt of contributing to the loss function. Okay, so the weight change rule is pretty intuitive in that sense. Now we come to the very important question of how do we change the weights in the hidden layer? So we have this neuron here, Jth neuron, which is in the hidden layer. The ith neuron is feeding it. The problem for hidden layer neurons, you have seen it from discussions before, XOR discussion, is that for hidden layer neurons, the target value is not known. We know the target value only at the outermost layer. The target value is not known. So T minus O cannot be computed for the hidden layer neuron. So what do we do? This particular step was a very important step, or this particular solution to the problem was a very important milestone in the whole history of AI. Okay, the notion of error backpropagation. Okay, it was first invented in 1962 and then again became prominent in 1984. 1962, I believe this was in Europe. 1984 was in MIT. Maclellan, Rumelhart, Hinton, okay, they contributed. So how do I change this weight? That is the question. Okay, here a very nice idea is used. The universal rule of backpropagation stays the same. Delta WJI is eta into delta J into OI. Delta J by definition is minus delta E delta net J. Which net J? Which net J? The net J of this Jth neuron. Okay, the net J of this Jth neuron. Notice that net J does not directly contribute to the loss. Okay, it contributes to the loss through the output of the Jth neuron, and that output forward propagating to the outermost layer. The error is observed in the outermost layer. But from the hidden layers, a little bit of error gets accumulated and contributed to the outermost layer. So let's see. So delta E, delta net J. Now delta E, delta net J is is converted to delta E delta Oj into delta Oj delta net J. What is this quantity? Delta E delta Oj, this is the output of the jth neuron. So we are moving closer. We are moving closer to the output layer where the error is observed. And delta Oj delta net J is nothing but the station derivative, the derivative of the sigmoid neuron. So delta E delta Oj is kept here. Oj into 1 minus Oj is the derivative of the sigmoid. Now delta E delta Oj. Here we make an interesting physical observation. What is the role of this Oj? The role of this Oj is to affect the net input of all neurons in the next layer. This Oj affects the net input of all neurons, each and every neuron in the next layer. Okay, so delta E delta Oj can be written as delta E delta net K into delta net K delta Oj, summing over all the K neurons in the next layer. It's quite intuitive, right? So this Oj is affecting the net K of every kth neuron in the next layer. Okay, so therefore I can introduce net K delta A delta net K into delta net K delta Oj. We have to obey the laws of partial derivative. We have to take the sum of all the contributing net Ks. So then I get minus sigma K in the next layer, delta A delta net K into delta net K delta Oj. Now this expression is quite nice. Delta A delta net K by definition is minus delta K. Okay, and delta net K delta Oj will be WKJ. WKJ, this weight. Okay, so what we get is this particular quantity, which is nothing but the delta K in the next layer multiplied backward by the WKJs. Okay, so if you want to picture it, all the delta Ks which are fed back by the weights backward, used backward to obtain the delta J here. That's why this algorithm is called backpropagation. Okay, this algorithm is called backpropagation. People at the back, the last bench, please stop talking. This is a very important discussion. Okay, we are going into the heart of backpropagation. Why the algorithm is called backpropagation? Please understand that. So these delta Ks in the next layer are summed over the weights backward, and the delta J in the previous layer is obtained. So that's why it is called backpropagation. And this you probably are tired of hearing me say this again and again. The most important invention for deep learning systems. So what we get is delta J is summation of delta K's with weights backward and the station derivative. Which station derivative? Which station? This particular neuron. We are interested in finding the change in weight for this connection. That is obtained from summed delta K's coming backward and the input for this connection coming from I and my learning weight. That's all. Okay, so then we finally have, so this is a recursive equation. Delta J is in terms of delta K's from the next layer. So delta K's from the next layer are obtained from next to next layer. Finally, where does the recursion stop? It stops at the outermost layer. Okay, and in the outermost layer, the delta K is completely known. In the outermost layer, the delta K is target minus output into station derivative. For any layer below outermost layer, it is backpropagated delta into station derivative. Okay, and the expression is very, very general. The station derivative can be for sigmoid, for ReLU, for linear neuron, anything. Any question? Okay. No question. So now this can give rise to what is called the vanishing exploding gradient. We'll come to that. Let me see if I have an example to illustrate the backpropagation rule. Let us see. An example. There is a pure feed-forward network 222. So this convention is used in deep learning. 2 for input layer neurons, 2 for hidden layer neurons, 2 for output layer neurons. So 2 input, 2 hidden, 2 output neurons. Input neurons are called X1 and X2, right to left when drawn on paper, X1 to the right of X2. Similarly, hidden neurons are H1 and H2, right to left. The output neurons are O1 and O2, right to left. H1 and H2 are ReLU neurons. O1 and O2 form a Softmax layer. So ReLU function, let me define it later. Let us just understand that ReLU neurons have gradient 1 going from 0. And before 0, it is a flat line. Okay, so there is a knee at 0. Then y is equal to x is the equation. And y is equal to 0 is the equation before 0. So the derivative does not exist at 0. It is forced to be 0 at 0. But before 0, the derivative 0 is 0. And above 0, the derivative is 1. Okay, ReLU is used to solve the vanishing and exploding gradient problem. We'll see how. But now let's work on this problem. So we have 2 neurons, O1 and O2 in the outermost layer, H1 and H2 in the hidden layer, X1, X2 in the input layer. So the error is a cross-entropy loss. So by definition, this is T2 log O2 minus T1 log O1. So okay, so we know that for Softmax, and this is Softmax, okay? For Softmax and cross-entropy combination, the change in weight is equal to delta. Change in weight is learning rate into target minus output into the input. Okay, so if I take W11, okay, 2 means the second layer. The change in weight must be learning rate into T1 minus O1 into H1 by the universal rule. What about the hidden layer? You might say that we have not derived the hidden layer weight change rule for cross-entropy and Softmax or cross-entropy and ReLU. Well, it is this way. You use the concept that the delta value is backpropagated. So delta value for cross-entropy and Softmax is T minus O. Okay, T minus O. So for this particular weight, W111, this particular weight, what will be the change in weight? Learning rate into the input, okay, X1, into backpropagated delta. So the backpropagated delta is T2 minus O2 multiplied by the weight used backward, this weight. So T2 minus O2 into W221, this weight, into T1 minus O1 here, multiplied by W211, this weight used backward, into the station derivative at H1. Station derivative is R dashed H1, where R is the ReLU function, multiplied by, it should be X1. Okay. So this example should tell you how to use backpropagation. Okay. Just one more time. The change in this weight, which is from the input layer to the hidden layer, must be equal to eta into delta here multiplied by the input. The delta here is sum of the backpropagated deltas. Here, the backpropagated deltas come from the next layer, which is the outermost layer. Two deltas have to be backpropagated. One from O1, the other from O2. Okay, and the backpropagated delta is T minus O, T2 minus O2, T1 minus O1. And we cannot forget the station derivative, which is the derivative of the ReLU function at H1. Is it clear how backpropagation operates? And it is very universal. Do not try to take any derivative in your Python code. Just use this expression. Okay. So now let's move to the vanishing and exploding gradient problem. So this becomes quite intuitive. If you remember how the delta values are obtained. The delta value here is backpropagated deltas coming from here multiplied by the station derivative. The delta value here will be the delta values coming backward multiplied by the station derivative here. Notice that the backpropagated delta already has a station derivative in it. So isn't it the case that if this path is long, by the time we come here, the derivatives, okay, the derivatives of this neuron, the derivative of this neuron, these, all these get multiplied. Okay. By the time I come here, all the derivatives from the upward layers keep getting multiplied and get accumulated here. Now, all these derivatives, at least for sigmoid neuron, these derivatives are between 0 and 1. So you keep multiplying fractions. Okay. And by the time I come here, these fractions are continuously getting multiplied, and then the delta value becomes small. And we know that in deep learning systems, these layers are very large in number. The network is very deep. So as we move towards the input layer, the delta value becomes smaller and smaller. So much so that after some time, the change in weight becomes negligible. So after a point of time, the layers will not see any change in weight. Thereby, the learning will be impacted very badly. So this is called the vanishing gradient problem. What vanishes? What vanishes is the delta value because of the progressive multiplication or accumulated multiplication of the station derivatives. How does ReLU solve this problem? ReLU's properties, zero derivative is either 0 or 1. Either 0 or 1, nothing else. Okay, so the delta value which is ultimately obtained at the outermost layer, either gets multiplied by 0 or gets multiplied by 1. Okay, so none of the station derivatives reduce the value of delta progressively. It either passes directly or it makes it completely 0. So one might come back and say that, well, it can multiply it by 0. And what will happen in that case? Now, this takes us to drop out stochastic gradient descent, those variations of gradient descent algorithm. Okay, what is the proportion of neurons which will have this behavior of contributing 0 to the gradient? Most of the neurons, I mean, it is never the case that all neurons contribute 0. Okay, they of course will lead to the disappearance of gradient in the previous layer. But if they pass a gradient, that will be exactly 1. Okay, so it is multiplication of either 0 or by 1 solves the vanishing gradient problem. Okay, probabilistically speaking. It's an interesting question. What proportion of neurons will pass the gradient as such? What proportion will completely block it? But it is either complete blocking or complete passage, not like sigmoid, which gradually, slowly, reduces the gradient and causes it to vanish. So vanishing, exploding, how can it explode? You think about it. Exploding gradient comes from a variation of sigmoid neuron called tan H, okay, tan hyperbolic function. And the tan hyperbolic function also can be scaled with k, some k value. So that can lead to exploding gradient. So vanishing gradient problem was practically observed when larger and larger and deeper neural networks started getting used. And then came something called LSTM, long short-term memory, especially for recurrent neural networks. Okay, neural networks which are used for processing sequences. There, the vanishing gradient problem was hitting the AI systems very hard. And then came LSTM. And LSTM was a very cumbersome network. And then came other networks like Transformer, for example, but that's a different story. We will, temporarily suspend discussion on neural network after backpropagation. You will do a substantial assignment in the class on training a backpropagation network on a data. So maybe the data is iris data or MNIST data, we'll see. Okay. But you will also have to observe the behavior for XOR function and other functions, which will be told to you. Okay, so let's proceed a little further.
Yeah.
A lot of
data will get lost because of multiplying by 0. So like isn't we like we are reducing some neurons which are actively learning,
which contribute to learning. The point is that if you have a very large network, it has been empirically observed that neurons which have gradient value 0 are not so many actually. Okay, it has been empirically observed. I have not seen any theoretical proof as such. Yeah, and also there is this dropout phenomenon where neurons are removed, from the network, and weight change rule or the learning process is applied only to parts of the network. Okay, so now here a point is pertinent. So all of you are probably aware of the excitement that DeepSeek is contributing. Okay, so the DeepSeek's secret is based on 4 things. One is mixture of experts. So mixture of experts is different parts of the neural network do different jobs. Okay, so just like the brain computes visual information at the back of the brain, auditory information on two sides of the ear. Okay, higher brain participates in other important functions like maths, language, music, and so on. It is not the case that the whole brain participates in computation, in information processing. Never the case. So apparently DeepSeek made use of that particular idea. It is not a new idea, it is an old idea. Second idea they used was distillation. Okay, distillation idea. So that is a different topic. Then another idea that was used is probing the architecture of the deep neural network. Which neuron is doing what? Which layer is actually contributing? Okay, so those points were made use of in a very clever way. Okay, not everybody understands what was going on. They have an archive paper on the internet. You are strongly encouraged to look at that paper because it's mainly neural network training based on backpropagation, essentially. But take a look at that. And the fourth idea I'll have to see. Okay, these three ideas. The fourth idea was, does anybody know? Mixture of experts, distillation, probing in the architecture, and one more. I'll have to look at it. Okay. So now working with ReLU. ReLU is a rectifier linear unit. And ReLU's definition is y is equal to ReLU x, which is max of 0, x. And dy dx is 0 for x less than 0, 1 for x greater than 0, is equal to 0. It is forced to be 0 at x is equal to 0, though does not exist. So the ReLU function's shape is like this. So if the output neuron is sigmoid and the hidden neurons are ReLU, now one question I think you will ask in the class is, in the lab, is what should we use for hidden layer neurons? For hidden layer neurons, use sigmoid. Okay, don't have to worry about ReLU now. Okay, for today's lab, don't have to worry about ReLU. So output is sigmoid and the hidden neurons are ReLU. The universal rule of change of weight is eta delta j oi. So the error function is total sum square loss. So the change in weight is eta into difference into sigmoid derivative into input on the connection. For hidden layers, it is this way. Delta WJI is eta delta j oi. Delta j equal to minus delta A delta net j minus delta A delta oj into delta oj delta net j. This minus delta A delta oj into 1 or 0. Okay. So for hidden layers, we are using ReLU neuron. So delta oj delta net j is going to be 1 or 0. Which is equal to minus k going over the next layer neurons, which is delta E delta net k into delta net k delta oj into 1 or 0, which is minus summation of backpropagated deltas or 0. Okay, so the backpropagated delta that arrives at the hidden layer neuron is either sum of delta values or 0. Because the station derivative is that way. So now, if I take this neuron, okay, if I take this neuron, then it totally depends on what is the net input arriving at this neuron. Okay, so if the net input is not 0, and if the net input is not negative or 0, then the gradient is 1. And the backpropagated delta, which is arriving here, pass downwards exactly undisturbed, unattenuated. And if the station derivative is 0, the input value for this neuron is non-positive. Then what passes down is just 0. Okay, and only this neuron is doing so. Other neurons, all of them doing this is unlikely. Okay. So the interesting derivations can be obtained from Softmax, Cross-entropy, ReLU combination. Okay, which we can take up later. Let me stop here today.